Hello, hello, hello. How's it going?
Hey, how you doing?
All right. Ugh. Fucking thing. Bum, bum, ba-dum. All right, it looks like it's post time here. Might as well get started. How's everybody doing?
Good, thank you.
All right, it's good to hear it. All right. Last class we started on physics and thermodynamics, and we went through some of the math that you might see. Just to give you an update, on the typical second fireman's exam, there's going to be 5 to 8 math questions, math problems, if you will. All right. They're all covered in the homework. All right. So I think Jolene will back me up on this, that if you do these homework questions, you can do these problems. You're going to be well prepared for the any math that comes up on the state exam. Is that true, Joe? Or?
Yeah, like I said last time, they worded a little differently, but it's literally exactly what's in here.
Okay. I thought we'd start off tonight by just going over those math problems. Make sure everybody has got a pretty good handle on how to do these problems. All right. So I don't know how many of you got a chance to do them or even look at them. I know it's been a kind of a quick turnaround here since Monday, but I just gotta have a warm, fuzzy feeling that at least you know how to solve these type problems. So let's start with problem number 1. Convert 100 degrees Celsius to degrees Fahrenheit. Can anybody tell me what the formula for that is?
Celsius times 1.8 plus 32.
Degrees Celsius times 1.8 plus 32 is correct. All right. In this case, 100 times 1.8 gives you 180, plus 32 gives you 212. The boiling point for both scales, 100 degrees Celsius is equivalent to 212 Fahrenheit. Good. So again, traditionally for the last almost 7 years now, they've stuck to the boiling point and the freezing point in these conversions. That doesn't mean any given day they can't deviate from that and ask you just an odd number and convert it to Fahrenheit or Celsius. Does everybody get that? So I think it's important that at least you get the formula. All right. I don't think you're going to need it because they haven't changed their tune since the test began, but you never know. All right. How about for converting Fahrenheit to Celsius? What's the formula?
You could minus 32 and then multiply it by 0.5556.
Minus 32 and what?
You could multiply it by 0.5556. That's basically the decimal equivalent of the fraction 5/9.
Okay. All right. Yeah, not what I had in mind, but yeah, that would work. Or you could subtract 32 and divide by 1.8. All right. That's less stuff to remember, right? All right. Multiplication or division. So in this case, it would be 32 minus 32 equals 0. And if you divide anything into 0, what do you end up with? 0 is correct. All right. So 32 degrees Fahrenheit is equal to 0 degrees Celsius. All right, good. I'm glad you're all on board with that. All right. Question 3 says, what pressure is exerted by a column of water 10 feet high? Anybody?
4.33 psi.
4.33 psi. Okay. You can multiply 10 feet by 0.433, or you can divide 10 feet by 2.31. Any questions on that? All right. That's a problem that's going to come up on every state exam. All right. How about the area of a 4-inch diameter circle?
12.56 inches squared.
12.56 square inches. Right? You don't have to do it any set way. Remember, a lot of you learned area equals pi r squared. All right. Today, if you ask a fourth grader, they're teaching them the area equals diameter squared times 0.7854. 0.7854 is simply pi divided by 4. They don't care which way you do it. The answer is going to be the same. All right. So you got 12.56 square inches. How about number 5, the circumference of a 6-inch diameter circle?
18.84.
18.84 what?
Would be inches.
Inches. It's one dimensional. So it's the area around the circle, the outside of the circle. It'll be in inches. All right. Question 6, they ask on every second fireman's state exam. It's a volume question. They want to know that you can calculate volume. So they give you an imaginary room 10 feet long, 8.5 feet wide by 7-foot ceiling. What I told you last class was all you need to do is multiply the 3 dimensions together. All right. So 10 times 8.5 is 85, times 7 is 595 cubic feet. All right. That is the volume of that room. All right. And later on in this same homework, there'll be a problem where they ask you the volume of a tank. All right. Question 7 is their fuel oil delivery question. This appears on every second fireman's exam. All right. You're expecting a fuel oil delivery of 6,800 gallons. Your tank holds 10,000 gallons. What is the maximum amount of oil you can have in the tank? Okay. The key thing to remember is here, you don't want to fill the tank up to the very tippity top. You got to have a little bit of room for error. All right. This is especially true in fuel oil because typically they have to heat it up to pump it and to transport it. That means it's usually heated up to 110, 120, sometimes 130 degrees. That changes its specific volume, how much space a gallon of that oil occupies. All right. So typically they'll give you a number slightly less than filling up the tank. In this case, 3,100 gallons. Does everybody kind of get that? All right. All right. All right. Number 8 is just an association question. Nobody measures tank in cubic inches, but in this problem, which appears on a lot of third engineers exams as well, they have that imaginary tank, 2,310,000 cubic inches. And then they go on to ask you, how much does the water weigh? What they're hoping you do is recognize that 231 cubic inches is 1 gallon. So if you divide the 2,310,000 by 231, you'll get 10,000 gallons of water. You know that a gallon of water weighs 8.33 pounds. So 10,000 times 8.33 will get you 83,300 pounds. Any problem with that? When that question appears on the state exam, usually the one right after it is just like it is here, number 9. A 10,000 gallon tank is half filled with water. How much does the water weigh? So you know it's half of 10,000, 5,000 gallons. All right. It's half of 83,300 pounds. 41,650. All right, or 5,000 times 8.33. All right. Number 10 is the volume question. They have a tank 10 by 10 by 10. The first version of this question, you know what the question was? If the tank has dimensions 10 by 10 by 10, is it a cylindrical tank or a square tank? They realized that was a gimme. All right. So then they asked you to, how much does the water weigh in that tank if it's filled? All right. Now, what I told you last class, does the temperature matter? It does not. All right. So in any one of these problems, they can tell you that the water is at a certain temperature, usually 60, 70 degrees, somewhere around there. It doesn't matter. All right. So anyway, if you take the 10 by 10 by 10, you get 1,000 cubic feet. You probably remember that there's 7.5 gallons in a cubic foot. That would give you 7,500 gallons in that tank times 8.33 will get you 62,475 pounds. All right. Or if you remembered that a cubic foot of water weighs 62.5 pounds, all right, then you could multiply that by 1,000 cubic feet and get 62,500 pounds. All right. What you'll take your cue from is the choices they give you in the multiple answers, the multiple choice answers. Remember, you're taking a multiple choice test. There's going to be 4 answers for every question. Your objective is to select the best answer. Does everybody kind of get that? Right. So they are sticklers for accuracy. So the answer might be 62,480 pounds. All right. Standard pressure, of course, is atmospheric pressure, 14.7. All right. And the device that measures that is the barometer. All right. Now that you know what that measured, did anybody look at their phone today and see what barometric pressure is?
For the one today
Yeah.
in Boston, it was at 29.32.
Excellent. Excellent. Out here in the sticks where I live, 29.84. That was about 5 minutes ago. So, all right. But that's good. All right. Number 13, we've beat up enough. Everybody knows how many turns for a slow opening valve to be full open. More than 5 full turns. All right. Question 14, they're talking about latent heat. We'll talk about that a little bit more tonight. Hopefully that'll clarify any questions you have about latent heat. Number 15, we'll talk about again tonight. It's going to take 970 BTUs to change a pound of water at 212 into a pound of steam at 212. All right. 231 cubic inches is 1 US gallon. There are 7.5 gallons in a cubic foot. There are 778 foot-pounds of work in 1 BTU. All right. Standard pressure, we just talked about it, the barometer, 29.92 inches of mercury on a standard day. And a column of water 2.31 feet high exerts 1 PSI at its base. All right. Now, I don't know if anybody remembers this, but the only math question I didn't put on this, I covered back when we talked about boilers. All right. They may ask you to calculate the heating surface of a tube. Does anybody remember that discussion?
Yep.
And how would you calculate that?
Diameter of the tube. the outside diameter, I believe, in the inside diameter, and the length of the tube.
Okay. How about the circumference of the tube?
I'm sorry, circumference, that's what I meant.
All right, circumference of the tube. All right. Now, the only problem you're going to have there is that the diameter is usually in what dimension?
Inches,
And the length is usually expressed how?
feet,
So you got to convert one to the other so you can do the math. Heating surface is always expressed as what?
Square feet.
Square feet. Excellent. All right. So at the end of the day, you got to bring your answer back around to square feet. All right. All right. And that's it. All right. Right up through third engineer. That's probably the toughest math question you're going to get. How do you find the heating surface of a single tube? All right. So everybody kind of gets it, right?
Yep.
So I don't want anybody to come back and say, the math beat me up. I didn't nail all the math questions. All right, any questions on this math stuff?
Just if you could do a quick example of this heating surface, because I looked
Absolutely.
at one of them and I couldn't do it.
Okay,
So if you could
All
just
right.
explain it so
All
I could
right.
see it.
usually on the second fireman's test, the tube will have a 3-inch diameter or a 4-inch diameter, but it's always 14 feet long. All right. So picture a tube. Well, let's do 4 inches because it's easier. All right. So the tube is 4 inches. Kind of a shitty looking tube, but you get the idea. By 14 feet long. All right. All right. First step is to find the circumference. So 4 inches times pi.
.56.
12.56 inches. Now, I can't multiply inches times feet, so I have two choices. I can convert the length, 14 feet, to inches, or I can convert 12.56 inches to feet, which is the way I would do it because I'm lazy. Right? Does everybody get that? You don't have to agree with the fact that I'm lazy, but all right. So I would take 12.56 and divide it by 1. Sorry about that. Divide it by 12 and get. Sorry about that. 1.04 feet. Everybody buy that? And then I'd multiply that 1.04 times 14. I'd get 14.65 square feet. That's the heating surface of one tube. For third engineers, they might say to you, the boiler has 120 tubes in it. What is the total heating surface of all the tubes? And that's just a matter of doing what?
Multiplying that number by 120.
Yep, multiplying the 14.65 square feet per tube by the number of tubes in the boiler. All right. So circumference times the length is the heating surface of a tube.
Is that for both fire and water tubes?
Yep. Now,
Okay.
remember, the heating surface of a fire tube is going to be based on what dimension?
The inside?
The inside diameter. because the definition of heating surface says the side of the tube with the products of combustion. All right. In that case, because tubes are always expressed by the outside diameter, they would have to tell you the wall thickness of the tube, and you would have to calculate the inside diameter. And then you would use that inside diameter to find the circumference. All right. And then it's still the length of the tube. All right. Whether it's
Thank you.
inside or the outside, the length doesn't change. Any other questions? And again, that I think that's about as tough as it's going to get. So I'd like to think everybody's going to sail through this math stuff without any issues. Would you guys tend to agree or not? And I guess you don't have a lot of confidence in your math skills, so.
No, it should be straightforward.
Yeah. I mean, a lot of people are intimidated about taking the test, period. And they get a little nervous when it comes time to do math on a test. So anyway. All right, let's take a look at where we left off and let's continue to wrap it up for physics and thermodynamics. All right. I don't know what happened to this here. Hold on a minute. There we go. All right, I'd like to, I don't think it's necessary that we review anything we went over last class unless anybody has a question. Anything that we went over last week, specifically the definitions, all right? And by the definitions, I'm talking how heat is transferred, all right? Sensible heat, latent heat, all right? The latent heat of fusion, the latent heat of evaporation, the definition of a BTU, all right? All those definitions are fair game on the state exam, all right? As a general rule of thumb, they'd like you to know the critical pressure, all right? One word about this. This was calculated by a couple of guys around the time of the Civil War using a slide rule. All right. They have since run these numbers on a supercomputer at MIT. Some of the textbooks out today put the critical pressure of steam at 3208.2. Not a substantial difference. But if you see a discrepancy in your travels, that's the reason for it. All right. This number was hand calculated. All right. Significantly important is that it didn't change the critical temperature. That 705.4 remained constant, even when we ran it on a computer. All right. Now, there's a lot of stuff in this handout that applies specifically to first and second engineers. And a lot of these laws that deal with perfect gases, Boyle's law, Charles' law, you guys don't have to know for the purpose of the exam. All right. So we can skip over that. I'm sure that's not going to make you too upset. All right. They're not going to ask you questions about this stuff. All right. Same thing with the Carnot cycle, the Rankine cycle efficiency. All right. They're not gonna beat you up on that. All right. Napier's law, Dalton's law, Newton's law. These are all questions they'll ask of first and second engineers. All right. Some of you might be interested, some of you might know these, but they won't be on the test. All right. All right. Where I'd like to start tonight, though, is this picture right here. And the first thing I like to ask people is, do you recognize this picture? And the way I say that, kind of in a smart ass kind of way, is that this comes out of a fourth grade science book. All right. The fourth grade is when they chose to explain to you about sensible heat and latent heat. All right. But here's the interesting part of this whole drama. All right. For the purpose of our discussion, all right, the definition of a BTU began with this concept. The starting point for their discussions was 32-degree water. And the argument they made was this: 32 degrees equals 0 BTUs. Even though you and I both know there is heat all the way down to absolute 0. But for the purpose of the definition of a BTU, the starting point is 32-degree water. All right. And when they come up with the definition of the BTU, the only thing that they really were interested in was how much heat did it take to raise 1 pound of water from 32 to 212 degrees, the saturation temperature at atmospheric pressure. All right. That's the whole basis of the definition of a BTU. Does everybody follow this? It's kind of abstract, I get it. All right. However, the one thing that you should notice is this: the mathematical difference between these two numbers is what?
187.
180. All right. And that's how many BTUs it takes to raise a pound of water from 32 to 212 degrees. 180 BTUs. Now, why is this significant, or why should you even care about this? All right. Couple of reasons. One, if I told you I had a pound of water, and that pound of water was 100 degrees Fahrenheit, how many BTUs would it contain?
68.
Excellent. Who said that?
That was me.
68 BTUs. All right, does everybody get it? Because the starting point for their scale starts where?
32.
32. Beautiful. All right. Consequently, if I told you I had a pound of water and it had 150 BTUs, what would its temperature be?
182.
182. Beautiful. All right. So what's the solution to this problem is if you know the temperature and you subtract 32, you'll have the enthalpy in BTUs. All right. If you know the enthalpy and add 32, you'll have the temperature. Does everybody kind of get this? All right. It's pretty straightforward. Now, how abstract is this? Most other countries outside the United States don't buy into this. All right. So this is our own little thing. All right. Now, what confuses most people is this. A pound of ice. All right. If I took a pound of ice at 0 degrees and I raised its temperature to 32 degrees, it would take 16 BTUs. To melt that ice, I need 144 BTUs. All right, to make it 32-degree water. And yet, I'm being asked to forget about that and call 32-degree water the zero. Does everybody understand this? All right. Now, this is significant because one of the questions they asked third engineers is, if I gave you a pound of ice and I told you how many BTUs would it take to turn that into a pound of steam at atmospheric pressure, you would have to add up. Jesus. All these numbers, 16, 144, 180, and 970. Does everybody get that?
What would you call the 16 BTUs? Is there a name for it? No.
They're sensible heat. All right. And the heat that I added to that pound of ice to make it a pound of water at 32 is the latent heat of fusion. The 970 is the latent heat of evaporation. That's where I changed that water at 212 into a pound of steam at 212. All right. But here's the thing I'm trying to get you to buy into. All right. The heat that I add to the water from 32 is what they call sensible heat. And remember, the definition of sensible heat is heat that I add to a substance that causes a change in temperature that I can measure with a thermometer. Right. So as I add heat to that water at 32, its temperature increases. All right, all the way up to 212. When I add additional heat, specifically 970 BTUs, it doesn't change the temperature of the water. It only changes its state, latent heat. Right. On the state exam, they might ask you, can you give me an example of sensible heat? All right. And you would say, the heat that I add to a pound of water at 32 to bring it to the saturation temperature, sensible heat. All right. All right. Example of latent heat, you can use either the ice at 32 to water at 32, or water at 212 to steam at 212. All right. Everybody kind of buy into this. You bought it once before in the 4th grade. All right. And then you probably found no further use for it as you figured you got it. I understand that completely. All right. But just remember, if you're going for third engineer, that's the question they'll ask you. For that example, they're asking you to include these values, even though the definition of a BTU actually starts with 32-degree water. And their argument was always this: we're never going to add water cooler than 32 degrees to a boiler. All right, so that's the reference point they chose. All right. Whether it's rational or not, you and I can talk about. Right. All right. Let's talk about, let me go back here, sorry. Enthalpy, all right? Now I'm trying to get kind of steer this towards a discussion about how many BTUs are in a pound of steam, all right? And again, the way we measure BTUs is by the term enthalpy. And that's the heat content or total heat of a substance expressed in BTUs per pound. All right. To make steam, what's the first thing I have to do?
Create saturated.
Excellent. I have to bring the temperature of the water to the saturation point. All right. What's always going to be the starting point?
We can reference 212, assuming the pressure's right.
No, the starting point for my water,
Oh, 32.
32 degrees Fahrenheit. All right. That's represented, the sensible heat is represented by HF. All right. HFG is the enthalpy of latent heat. That's the heat that I have to add to cause that pound of water to change into a pound of steam. And you can see by this mathematical equation that the heat that I add to the water plus the latent heat equals the total heat, the Hg, in that pound of steam. Right? So when somebody asks you, what's the total enthalpy in a pound of steam? It's the sum of the heat that I added to the water plus the latent heat to change its state. All right. So the enthalpy in a pound of steam, Hg, is the sum of those two. That makes sense? All right. Now, to make sure you kind of get this, here's what they're fond of doing. All right. They're going to ask you a problem like this, and they're going to show it to you. HF plus HFG equals Hg. If that's true, what's Hg minus HF?
HFG.
HFG.
HFG. It's that simple. Does everybody get that? All right. So often, couple things we know about boilers. We know the total enthalpy in a pound of steam, and we know the enthalpy of the water in the boiler. If we know those two things, we can determine the enthalpy of evaporation, the latent heat required to change that. All right. All this information is in a document known as the steam tables. Has anybody ever seen one of these? All right. The steam tables tell us everything we need to know about steam. Okay. If you look at this example, and this is exactly the example, this page. Jesus Christ. That the inspectors have. All right. It only shows this much of it, but that's all they need for their discussion. In this example, the column to the left is the absolute pressure. All right. The temperature, they're going to ask you, what temperature is that?
Temperature, which water turns into steam.
No,
The temperature of the water?
excellent. More importantly, the temperature that water will do what?
Oil.
Boil. You know that because if you look at atmospheric pressure, water boils at what temperature? 212. All right. Okay. First exercise on this is to understand this concept. If the pressure goes down from atmospheric pressure, what happens to the saturation temperature?
Goes down as
Increases.
well.
It also goes down. As the pressure increases from atmospheric pressure, what happens to the saturation temperature?
It increases.
It increases. Everybody buy that? All right, pretty straightforward, isn't it? All right. All right. Now, if you go out here to this column where it says HF saturated liquid, the number 180 tells me what?
The amount of BTUs in the water
No.
before it steams?
Sensible heat,
The sensible heat to take water from what temperature to
Or
where?
sensible heat.
from 32 to 212.
The saturation temperature. All right. The 970 represents what?
This, the latent heat.
The latent heat. All right. And what is this 1150?
That is the in enthalpy,
Enthalpy.
enthalpy, okay, enthalpy.
All right. But even more simply, isn't it the
Total heat.
sum of those two numbers added together? Does everybody get that? All right. And let me give you a tip here. That's true at every pressure. The sum of the sensible heat and the latent heat equals the total enthalpy in a pound of steam. Right? Isn't it a beautiful thing? Right? All right. Now, if you look at this chart right here, at the critical pressure, 3203.6, all right, the liquid has 902.5 BTUs, and the steam has 902.5 BTUs, all right? What's missing here? There's no latent heat.
Yep,
Let me put it this way,
it says 0.
all right? At the critical pressure, water becomes steam without the addition of latent heat. All right,
This book says 3208.2.
yep. What, the steam table? The
Yeah,
actual steam table you got? Yeah, that's based on that calculation they did at MIT on a supercomputer saying those boys, Keenan and Keys, with their slide rules, they were wrong. Either way is fine. The state prefers you to use 3206, but they'll discuss it with you if you want to make a point. All right. All right. So what are they going to ask you about all this stuff on the test? All right. As the pressure increases, which is the column on the left-hand side, the total number of BTUs to bring the water to the saturation temperature also increases. And you can clearly see that all the way up to the critical pressure. The latent heat, the enthalpy of evaporation, all right, decreases as the pressure increases. And that continues all the way to the critical pressure, where latent heat is 0. All right. Here's the weird thing. The total enthalpy in a pound of steam increases for a little bit. And then somewhere right around here, the total enthalpy in a pound of steam starts to decrease. All right. What's important is that you get this, and that point is right around 460 PSIA. Right? And it took them decades to figure this out. But if you're going to operate a boiler above 460 PSIA, what do you need to do to make it worth your while? You need to superheat the
oh,
steam. That became the line of demarcation. All right. Think about it. A guy's operating at his boiler at 3,000 PSI. Each pound of steam only has 1,020 BTUs. The guy operating at 100 has 1,187 BTUs per pound. All right. Does that make sense? All right. So that 460 PSIA, that became the point where they had to superheat the steam to justify operating at that higher pressure. Right. Just to clarify this in your mind, all right, as the pressure increases, the column on the left, what happens to the saturation temperature?
it increases.
It increases. Excellent. And all boilers, unless they're equipped with a superheater, make what kind of steam?
Saturated.
Saturated steam. Excellent. All right. What's the highest temperature of saturated steam?
705.
705. All right. You can get superheat temperatures up to 1,000, 1,050 degrees, but the highest saturation temperature is 705 degrees. This shows it probably a little bit clearer. The enthalpy of evaporation, as the pressure increases, the enthalpy of evaporation does what? It decreases.
Yeah, past
Right.
15.
So they have a number of questions on the state exam where they're going to bounce this off you. All right. So as long as you've got it square in your mind, the saturation temperature increases as the pressure increases. It also decreases as the pressure decreases. Everybody gets that. It works both ways. The latent heat of evaporation decreases as the pressure increases, all right? And that's simply because, especially above 460, all right, the density of water and steam start to become closer and closer together, all right? And it takes less heat to convert that pound of water into a pound of steam, right? Any questions about this stuff? I realize there's a lot of stuff coming at you, all right, all at once. Now, the one thing that they're gonna make sure that you understand about the steam tables is this. The numbers that we see here for the enthalpy of the saturated vapor, the Hg, are for dry saturated steam. Okay, so these values are only good if the steam contains no what?
Water.
Water.
Water, no moisture at all, dry saturated steam. All right. All right. Now, does it make sense to you that if the steam contains moisture, will that hurt the number of BTUs in a pound of steam? All right. To show you how simple the calculation is, all right, if we took a pound of steam that had 3% moisture, we could calculate the enthalpy of that wet steam, but not the way you probably think. Many of you would say, well, let's just take 97% of the total enthalpy, and that's close enough for government work. All right. But the reality is, for me to make steam in the first place, what's the first thing I have to do? I have to get the water to what temperature?
Saturation, just.
The saturation temperature. There's no way around that.
Right.
All right. How I failed in my quest to get dry saturated steam, I didn't add all the latent heat. And it's not because I wasn't trying or I didn't care. Has anybody seen water boil? Is it nice and peaceful, or would you classify it as kind of violent? All right, chaotic. All right. When water boils, basically what happens is steam bubbles form closest to the heat. They rise up and overcome surface tension. All right. And they break free, become steam. What happens in that process? They often pick up little droplets of water, all right, which lowers the enthalpy of the steam because I gotta heat up that water, right, to the saturation point. So wet steam has a lower enthalpy, all right? And the calculation is the HF plus the percentage of quality times the HFG will give me the enthalpy of wet steam. And that's often expressed as HGW, indicating wet steam. All right. Now, the only other time they're going to ask you anything about enthalpy, all right, is a phenomenon that occurs in most steam plants. Has anybody ever heard of a PRV?
Pressure relief valve?
Close. How about pressure regulating valve? All right. Now let's pick on Dave Boyd. You work at the meatball factory, right?
Yeah,
All right, you make steam in a boiler at what pressure?
under 10 PSI.
Excellent. He makes steam in his boilers at 110 PSI. And that goes out to the meatball factory. And let's say the meatball machine uses steam at what pressure?
It would be the same pressure. It's coming, yeah, it comes out the same.
I don't know. Are you sure?
Well, they may regulate it down, yeah, to
Yeah.
control it for what we're baking.
That's right. And the way they do that is with a pressure reducing valve.
Right.
All right. A pressure reducing valve does nothing else but lower the pressure so you can utilize it in your process. Does that make sense?
Yep.
All right. One of the things that's weird about PRVs,
Bad cigarettes. Call from Bad Sig.
Hello, please leave a message after the tone.
sorry about that. All right. One of, I
That
don't
steam's
know.
all over the place. We need to get it under control.
Let me start again here. So a PRV, a pressure reducing valve, takes steam, which we normally produce at a constant pressure, and allows it to be reduced for whatever I need in my process. All right. And let's just say at Dave's factory, we drop it down to 50 or 60 PSI. I don't know, let's say 50. All right. Just for the sake of argument. All right. One of the laws of physics says this: steam passing through a pressure reducing valve does so with constant enthalpy. It's an isenthalpic process, which means a pound of steam at the low pressure side of that valve has the same enthalpy as the pound of steam on the high pressure side. It contains the same number of BTUs per pound. All right. Now, does that sound like a good idea to most people?
No.
Constant enthalpy, good idea?
No,
All right. Why?
seems like I'm wasting a lot of energy there.
Okay, you're on the right track. Clarify that. What do you mean by that?
Not sure. I just see this as we're losing energy because the entropy is latent heat. So I'm losing, if I'm at 110 and I'm down to 50, I've lost some energy.
Okay, you're exactly right. You're just not saying it good. All right. How about this example? I take the 110-pound steam that you made in your boiler and I pass it through a steam turbine and I drive a machine, a pump, a fan, a generator, and the exhaust pressure is 50 PSI that you need for your process. All right. What have I done in this example?
I've converted to mechanical energy.
I've done work. All right. The main problem with pressure reducing valves is that I got nothing to show for it. Alls I did is I dropped the pressure of the steam, all right, for my convenience, all right? But it's a dog with fleas. It's a huge energy loss, but it's the most widely used device in our industry. All right, does everybody
So
kind
what-
of get that?
Why not run it at a lower pressure? Why not run it at 50 and do away with the valve?
Well, part of the problem is this: the higher the pressure, the lower the specific volume of the steam. So I can transmit higher quantities of steam until I drop its pressure. All right. And I can do it more efficiently at higher pressures. All right. All right. Yeah, you're right. The problem is in your plant specifically, there might be different lines. All right. And there might be different pressure requirements for the different foods that you cook or whatever the hell you're doing over there. All right. So you might need 75 pounds over here, 100 pounds there, and 50 pounds over there. All right. You don't want to make steam at multiple pressures. You
Right,
can make it at one pressure. All right.
stop it.
But use PRVs to deliver it to the process.
So what happens to the energy? It's got to go somewhere.
Right? Well, remember when we talked about the first and second law of thermodynamics? All right. No machine is 100% efficient. This is a classic example. As steam passes through a PRV, it does so with constant enthalpy, but there's a gain in entropy. And entropy is the next topic we're going to talk about. All right. People figured out a long time ago that nothing's 100% efficient. There's going to be a loss in everything we do. All right. This is especially true when we utilize steam as the working medium. All right. The guys that invented the steam tables said, we're going to call that loss entropy. All right. And the definition that you and I can relate to is that it's heat unavailable for work. All right. Due to the fact that nothing is 100% efficient. All right. Now, if you go back to the steam tables, they have actually put a number on entropy. All right. A value. All right. This is where this gets a little abstract. All right. The value for entropy are BTUs per degree of absolute temperature. All right. So I can calculate specifically how much heat I lost in any process. Not that that matters to me and you, but it might matter to somebody that runs a meatball factory. All right. What's the gain in entropy as I pass steam through a PRV? All right. What the real value of entropy is, constant entropy can't happen here on planet Earth, but it gives them a baseline to compare the actual process to. In other words, this is what really happens. This is what should happen in a perfect world. Why is there a difference? And what can we do to make it better? All right, does everybody kind of get that? So it's really more theoretical stuff than practical, but it shows you that devices like PRVs, as Dave pointed out, he noticed it right away. They're not efficient devices. All right. All right. They're convenient for us. All right. But they're not really helping us out. All right. So here's the point. They're going to ask you, do you know the definition of enthalpy? And you're gonna say, yes, I do. It's the heat content of a substance expressed as BTUs per pound. If something happens with constant enthalpy, it's what they call an isenthalpic process. All right. For third engineers, they'll ask you, have you guys ever heard of entropy? All right. Entropy is heat unavailable for work. All right. That's how I'd leave it. And in a perfect world, everything happens with constant entropy or an isentropic process. All right. Any questions? Good. Now, a lot of this stuff in between you don't care about. All right. And they're not going to ask you. This is first and second engineer stuff. All right. But the steam tables themselves, there's just a kind of couple of fun facts that you need to remember. All right. The steam tables tell us the properties for steam at definite conditions. All right. There are 3 sets of steam tables. There is a temperature table, an absolute pressure table, which is the one you and I looked at, and there is a superheat steam table. All right. The 3 main headings on all steam tables are specific volume, enthalpy, and entropy. All right. Now, for third engineers, the question they ask is, can you tell me the 5 main headings on a steam table? And what they're looking for is absolute pressure, saturation temperature, specific volume, enthalpy, and entropy. So they ask third engineers a little bit differently. What are the 5 main headings on the steam tables? Okay. Now, the steam tables that you guys got don't list every pound 1 pound at a time. Is that true?
Yeah, that's true.
The guys that invented the real steam tables, this is a picture of it, Keenan and Keys. They did every single pound, 1 pound at a time, from a perfect vacuum to 10,000 PSIA. They calculated every one of these values by hand. Took them 30 years. And they had a pretty serious drinking problem at the end of that. All right. Now, the question becomes, if you can't find a value, for instance, if the inspector says to you, this is the steam table you have, all right? And he says to you, how would you find the saturation temperature for 17 PSIA? All right. Well, you can clearly see on this table that there's nothing listed for 17 PSIA, right? All right. However, the next best thing I have is I have a value for 15 PSIA and a value for 20. So I know that 17 is going to fall somewhere in the middle of that. All right. Everybody agree to this? All right. The mathematical function of finding an unknown value between 2 known values is what they call interpolation. Has anybody ever heard that term before? All right. How you would find that value is by interpolating. All right. All right. That's all they're going to ask a second fireman. In other words, they want you to understand the word. All right. So interpolation is finding an unknown value between two known values. All right. This page actually shows you how to calculate the enthalpy of steam at 132 PSIG. All right. And that falls between 140 and 150 in the step-by-step solution. They're not going to ask you to do that. All right. They just want you to understand the concept of interpolation. Everybody kind of get it? Right. Now, the funny thing is, the steam table, like that I have, I got at a flea market. All right. Some engineer dies, his widow sells all her stuff. All right. And these books by Keenan and Keyes are valuable, especially for the fact that they list every single pound, 1 pound at a time. So if you're ever at a flea market, a yard sale, and you see a Keenan and Keyes steam tables, you can probably buy it for 50 cents or a quarter, all right, off the widow that has no idea what she has, all right. They're actually pretty valuable, all right. In a bookstore, they go for 50, 75 bucks, all right.
Wow.
You could probably make a killing, all right. All right, a flash steam is the next topic. All right. Has anybody heard that term before, flash steam? All right. Any idea what it means?
Hot water going into a lower pressure.
Very good. Very good. All right. You and I have two ways of getting steam. If I boil water and make steam, that's what's known in this industry as live steam. As Greg says, if I take water in a boiler at 100 PSI and I let that water go down to a blowdown tank, for example, that's at atmospheric pressure, some of that water is going to flash into steam because it has a higher enthalpy than the saturation temperature at atmospheric pressure. All right. Anytime that happens, this is what we call flash steam. So no matter what I do, if I blow down the water column, the gauge glass, that water, once it hits atmospheric pressure, a portion of that water is going to flash into steam. All right. Make sense? All right. The only concern that you and I need to have is this. In my boiler at 100 PSI, if something happens, particularly a leak in the boiler, a hole in a tube in a water tube boiler, all right, the most dangerous thing that can happen is that the pressure drops rapidly. If the pressure drops very fast, the water in the boiler is gonna do what?
Flash.
It's gonna flash into steam. And that's gonna make my problem a lot worse. So what they recommend is this. In the event of a boiler leak, what you wanna do is close the main steam stop valve and try to maintain the pressure. Or rather, have it decrease gradually, all right? So the water has a chance to decrease in temperature as well. All right, if you ever get that mismatch between the saturation temperature, all right, and the pressure, all the water in the boiler can flash into steam. Right? And that's considered a pretty dangerous situation. And that's one of the reasons you're there, to recognize that and do something, all right? They haven't made a boiler yet that'll isolate itself, all right? Although the non-return valve does a pretty good job of isolating the boiler from any problems like this. Any questions? The reason there's a formula in here for flash steam is that sometimes they ask third engineers, how would you go about justifying replacing your blowdown tank with a flash tank? All right. And the justification would be how much steam you produce every time you blow down the boiler. You'll find that you make a lot of steam that's good in quality. It can be utilized in a flash tank, all right, making the payback of that equipment almost instantaneous, right? So this is how you would justify, how you'd sell it, all right? You can see in this example, if you blew down the boiler and you release 250 pounds of water, all right, you'd produce about 30.5 pounds of flash steam that could be directed towards the DA or could be utilized in other low pressure areas in the plant rather than have that steam go to atmosphere, go to waste. All right. So that's one of the ways that you justify doing that. Now, the Malia chart. Has anybody heard of this thing? All right. Your steam table comes with a Malia chart. And what the Malia chart is a confusing looking graph. All right. But at the end of the day, what this thing is a graphical representation of the steam tables. All right. So almost all the information that's on the steam tables is on the Malia chart. All right. One of the things they're going to ask second fireman is, have you ever seen a Malia chart and can you tell me what it is? And that's all they expect of you. All right. It's a graph that's a representation in graph form of the steam tables. The question they ask third engineers is, what are the lines on a Malia chart? And you can see they're listed right here. Lines of constant enthalpy, constant entropy, constant temperature, constant pressure, and constant quality. There's a saturation line and a degree of superheat. All right. One of the trick questions they ask about this is, what information can't you find on a Malia chart versus the steam tables? And the answer is, you can't find anything about specific volume on the Malia chart. All right. You can find everything else that you can find All right, in the steam tables. Now, does everybody see, watch this, this heavy black line that's about the middle of the Mollia chart? Everybody see what I'm kind of pointing at there? All right. What happens right here at this point to that black line? It
That's
drops
it.
off
It
rather
drops.
dramatically, doesn't it?
Yep.
Right here at the peak, guess what pressure that is?
460.
460 PSIA. All right. So that shows that rather dramatically what happens to the enthalpy in a pound of steam as the pressure gets above that. This black line is the saturation line. All right. So you can see the enthalpy, which are these numbers on the horizontal lines, enthalpy increases until it gets to that 460. And then it drops off rather dramatically. All right. That makes sense. All right. So you can see it graphically here when you look at the Mollia chart. All right. But if you work in a power plant, if you work maybe even at a meatball factory, a plant engineer would have a huge version of this on the wall in his office, and he would plot problems that are happening in the various processes in the plant. And it would help him identify maybe where the losses in this process are occurring. For instance, let me show you this one. Right here. See this straight line that goes right down? That's constant entropy. All right. And what did I tell you about constant entropy?
Doesn't exist.
Not going to happen. Excellent. It's not going to happen. This horizontal line, or this line that kind of slopes away, slants away, that shows the actual expansion of steam through a turbine from admission to exhaust. All right. So you can see as steam passes through the turbine, it gets further and further away from the ideal. All right. Entropy increases. All right. There's a loss or a gain in entropy, a loss in efficiency. So the object of the game, especially if you're a plant performance engineer, the plant engineer, is try to dictate or determine where that loss is occurring or why that loss increases. All right. From a slight change here to a greater change here. All right. Remember, steam turbines are closed machines. We can't see what's happening inside, but by plotting what happens on a Mollia chart, it helps them identify where in the steam turbine the losses might be occurring. So now that plant engineer might go to the maintenance guy and say, hey, next time you open up the turbine, I think steam is leaking in the 5th stage packing. All right. I think it's leaking by. So this is a tool they use to identify problems. All right. So that's why this Mollia chart is pretty useful in real world applications. I know a lot of you look at the steam tables and this stuff and say, that's so abstract. I'm never going to use that. But even in a meatball factory, all right, they would use a Mollia chart to figure out if they're getting the biggest bang for their buck. All right.
So how would you must have probes at different or temperature sensors or thermocouples at each stage of the generator or the turbine. Excuse me.
Yep. That's exactly right.
Okay.
That's exactly right. And that's why it's important that you grasp those concepts like thermocouples of pyrometers. That's how we measure stuff. All right. And yeah, we can't see this stuff, just like you probably can't see what's happening in a lot of the processes at your plant.
Right.
Right. But you know if it's working or if it's not. And so that's why these tools are useful. And they don't want you guys to be able to figure stuff out. I mean, the second fireman's only an entry level license, but they want you to understand there are tools available to you, all right, that help you do that, that figure out all this stuff for you. And it's pretty cool. And all right. All right, why don't we take a 10-minute break and then we'll come back and we'll talk about calorimeters. All right. So I'll see you in about 10 minutes.
To delete all old messages, press delete. Again, calls will not be answered. You have one new message, Wednesday, 6:56 p.m.
Been incarcerated in
Message deleted. End of messages.
from Matt
All right. Time to get back at it here, I guess. The next topic is pretty simple for everybody. For second fireman, all right. They only have one question in the database concerning this, and the question is, how do we measure the quality of steam? And the device or devices are known as calorimeters. All right. There are two types of calorimeters in this business. They work on different principles, but pictured here is what they call a separating calorimeter. And this works on a very simple principle that water and steam have different densities. All right. And what happens, that you can see in this illustration, steam from the boiler comes into the calorimeter. It hits this separator. All right. And the separator knocks the water out, which falls, or the moisture, which falls into this inner chamber. The steam, being less dense, gets redirected into this jacket, this outer chamber, and it passes through an orifice and is discharged to atmospheric pressure. All right. The moisture collects in the middle, and we can read the level of the moisture in a kind of a gauge glass on the side of the calorimeter. All right. Once we've done this, and this test only takes about 10 or 15 seconds. All right. We take the weight of the moisture and divide that by the weight of the steam plus the weight of the moisture. And that will give us the percentage of moisture in the steam. All right. Isn't it a beautiful thing? All right. Now, you're probably saying, I don't have one of those at my plant, or I've never seen one. That's because the boiler manufacturers today did these tests on your boiler at the factory. And when you bought the boiler, they told you your boilers are going to produce steam with 5% moisture. And you said, that's good for me. All right. All right. Do you have any idea, Dave, like the mirror boilers, what the quality of steam coming out of those is? You don't care, right? Yeah. You're making meatballs, right? The other type of calorimeter, and this is the more popular one, is called a throttling calorimeter. Same thing. This lets steam out of the boiler. It passes through an orifice into what they call a hot well, basically a chamber with a thermometer in it. All right. The steam passes through the orifice and exhausts to atmosphere. All right. The whole object of the game here is to read the temperature. All right. Once we get the temperature, we understand this, that at atmospheric pressure, it should be corresponding to that pressure, but the temperature is actually going to be higher, all right, because it's coming from the boiler, all right? So what we'll do, this is a classic example of how we can use the Mollier chart. We will plot what happens here on the Mollier chart, all right? And this will tell us the percentage of moisture in the steam. This is much preferred over all other types of calorimeters because there's no mathematical formula you have to do. You plot this on a Mollier chart, all right? So this is the more popular of the two. Now, for third engineers, the question they're going to ask is, how do they measure the moisture and steam? A calorimeter. Can you name two types of calorimeters? All right. So now you've seen them both, a separating calorimeter and a throttling calorimeter. They're not going to ask you how they work. All right. or what principle they work on. They're not going to ask you any specifics. All right. They understand that this is kind of old school stuff, that when you buy a boiler today, the manufacturer is going to tell you this boiler is going to make steam at 96% quality all day long. Does everybody kind of get that? All right. Nobody really bothers doing this anymore. All right. I'm sure, Dave, you don't do it at your plant, right? I can't hear you, but
We don't do it at our plant, but you're
Yeah.
giving me an idea because product quality is always an issue. And this may be a tool I can use to take a look at what we're putting down for
Yep.
temperature and moisture ratios in the product.
excellent. Yeah. Especially in a process where you're actually cooking the product, you might not have enough enthalpy in the steam if the product's coming out, bad or uncooked or whatever happens. Yeah.
Well, it affects the thickness or the density of the product, believe it or
Okay.
not.
Yeah. Yeah, I buy that. Yeah. So there's a lot more to it than just cooking meatballs, right?
Yeah.
There isn't
And the
some
same-
guy there with a chef's hat saying this is perfect. Yeah, yeah. Yeah, I imagine there's a lot more science to it than anybody really thinks about. And that's a beautiful thing, that's why you guys are in business making the big money, people love meatballs.
Actually, the biggest selling thing there is this thing's called chicken roller bites. I'm dead.
Sounds
serious.
yummy. Yeah.
It's like ground up chicken made into a hot dog, but with breaded on it. And we're 100,000 cases behind, and we're falling because so many companies want this thing.
No kidding. No
Yeah,
kidding.
they're delicious.
Do
like
they
I said,
sell them in a vending machine or is that the supermarket or?
7-Eleven and Cumberland Farms.
Really? Really?
Those they roll in there in the little hot dog rollers. Yeah, those
Yeah.
things. Those things sell like you would not believe.
Really? Yeah. I stopped at a Cumberland Farms today. It didn't occur to me to select my lunch from their choices,
I call it gas station food, but you know what?
Yeah.
That gas station food's putting some serious money on the
Yeah,
table.
yeah, obviously. Yeah. 100,000 cases going out the door, right?
Yeah, we're working 7 days a week running that machine. We still can't make enough. We're gonna be opening the second plant just simply to make these things.
No kidding.
Yeah.
Well, that's good. Business is booming.
But to your point, you can put more meat into it or you can put more moisture into it.
Yeah.
And that goes back to the steam, how much we're putting in there. And I would venture to guess the rate of saturation is a key factor too. And now that we're looking at that, I can see the relationship. So it will be something I will be questioning
Yeah.
quality control on, because that falls under my realm as well.
Yeah, and as part of that, you can look up and or ask Mura, hey, what quality steam do these puppies produce, and does it decay over time, or is it something I should be concerned with? These
Yeah.
devices that I just showed you, these calorimeters, are simple devices.
Yeah.
And it doesn't take a rock scientist to figure out how they work, but you can get some valuable information from them, and it's important. Especially if you guys are going through PRVs. If the pressure on the high side of the PRV varies, then the pressure on the low side will vary as well. And that could be another issue. And so.
It is that you mentioned it. We got temperature variations in the oven. I was actually the one who discovered that. And I said, well, when I get to it on my table of lots of other problems, we'll get to that. But these two things may be related, actually.
Yeah. So, yeah, at least you got some information out of this. And, and again, I just want to alert the second fireman. There's a lot of stuff in this handout that doesn't apply to you, that they're not going to ask you about. Again, you're an entry-level guy. I'm just touching on the stuff that they have in the database of questions. So they touch on a broad range of stuff in thermodynamics and physics, but basically they want you to know the basics, sensible heat, latent heat, the definitions of a BTU, things like that. All right. And I just kind of brushed over steam tables, Mollia charts, things like that, just so you've heard of them. All right. You're not going to have a long discussion with the inspector about the Mollia chart. All right. And but you're not supposed to. You're not supposed to know about that stuff until you're well into this business. So that's what we're looking at. Anyway. All right, I just want to make sure, did I cover everything that's on the homework? Oh, I don't think I did. There's one thing I didn't cover. All right. And let's take a look at the homework real quick. All right. The things that are the definitions, I think we covered pretty well. All right. The one thing I didn't cover or I haven't talked about yet is question 15. It says, how many BTUs are required to raise the temperature of 100 gallons of water from 50 to 150 degrees? All right. Now, what's the key to this question? What's the first thing a sensible person would do? Say it again, Jeff.
Well, isn't it 90 BTUs to raise 1 pound of water 1 degree?
It's 1 BTU
All right.
to raise 1 pound of water 1 degree Fahrenheit. So the difference in temperature is your first key. How much of a temperature rise is there?
100.
100 degrees, right? All right. So I need 100 BTUs per pound. But that's the tricky part of this question. All right. You don't have 100 pounds of water. What do you have?
100 gallons, but you can convert
100
that.
gallons. And remember, enthalpy and the definition of a BTU all deal in pounds. So step one would be to do what?
Convert gallons to pounds.
Convert gallons to pounds. All right. So 100 gallons is 833 pounds. Everybody buy that?
Yep.
And it's 100 BTUs per pound. So you multiply that by the number of pounds to get 8333 BTUs, right? Everybody in agreement?
Yep.
But I think we covered just about everything else on this. How about question 13? Where would you find information about the enthalpy and specific volume of steam?
Steam tables.
The steam tables. All right. And that's as deep as they'll get with second fireman about the steam tables. All right. By the time you're going for your thirds, they're going to ask you a little bit more. What are the headings? All right. They're probably figuring that you've been around this business a little bit now, and it's come up at your plant or in discussions at your plant. So that's the way of this business. All right. Any other questions before I let you go for the night? So homework 4 is going to be due on Monday. I sent you the answers to the math problems right now. So you should get that momentarily. Anything else before me? Have a nice weekend. Stay out of trouble. I'll see you on Monday.
See you on Monday. Thank you.
Thank you.
All right.
Mr. Walker, you got a moment?
Yes, absolutely.
Hey, so going on vacation next week.
Okay.
Not sure if I'll be able to make it to either classes. Do you want me to send in the homework and all that?
Nope,
Sunday.
just stay current with the homework. Make sure you get it done I send you the answers to the homeworks anyway. But what will happen, Stacy will send you the videos of the class,
Yes, sir.
and maybe when you get back from vacation, you can just review them. All right.
Roger that. I'll just do
Yeah,
that then.
that's all there is to it. But I appreciate the heads up that you're going. Where you going on vacation?
Going to Myrtle Beach.
All right. Are you a golfer?
No, I got 3 kids. Just trying to take them out of the house.
All right. That sounds like a nice destination.
Yeah. Well, it said it might rain the whole time, so hopefully when it changes. But
well, have a
the
good
hotel
time,
does have an indoor pool, so as long as
Oh,
there's
there
a
you
pool,
go.
that's all I care about.
There you go. Yeah, kids don't need much, you know.
No, food and water. That's it.
All right. Well, enjoy your vacation. I'll see you on the other side.
Yes, sir. Thank you very much.
All right.
All right, take care.
All right. Bye.